Hello, everyone. I will introduce our CVPR work, SMAE. Few-shot learning for HDR deghosting with saturation-aware masked autoencoders. To generate an HDR image on dynamic scenes with only few labels, we propose a novel semi-supervised approach to realize few-shot HDR imaging via 2 stages of training. Unlike previous methods, directly recovering content and removing ghosts simultaneously, which is hard to achieve optimum, we first generate content of saturated regions with a self-supervised mechanism and then address ghosts via an iterative semi-supervised learning framework. We also propose an adaptive pseudo-label selection strategy to pick high-quality HDR pseudo-labels, such as well-exposed and ghost-free samples, in the second stage to avoid the effect of mislabeled samples. As we know, HDR imaging can effectively recover details in static scenes. It may produce ghosting artifacts on dynamic scenes or handheld camera scenarios, especially when saturation, motion are existed. In this paper, we try to generate ghosting-free HDR image with a few labeled data. Although we can produce pleasing results with a large amount of samples, it's challenging to collect these HDR labeled data, such as requiring an absolute static background, conducting manual post-examination. Recently, FSHDR trains a preliminary model and generate HDR pseudo-labels, then use synthesized artificial dynamic LDR inputs and pseudo-labels to train the network. However, they suffer from several problems. This approach expects the model to handle both the saturation and the ghosting problems simultaneously, but it is hard to achieve under the condition of few labeled data, especially misaligned regions caused by saturation and motion. In addition, the errors in optical flow further intensify the degraded quality of artificial dynamic LDR images, resulting in an apparent distribution shift between LDR training and testing data which hampers the performance of the network. Motivated by divide and conquer, a reasonable way is to address the saturation problems first and then cope with the ghosting problems with a few labeled samples. In this paper, we propose a semi-supervised approach for HDR deghosting, named SSHDR, which consists of 2 stages: a self-supervised learning network for content completion and sample quality-based iterative semi-supervised learning for deghosting. This is the framework of our method. We pre-train a network to generate content of saturated regions by self-supervised learning. Based on this network, we propose a sample quality-based iterative semi-supervised learning approach that learns to address ghosting problems. Inspired by MAE, considering that the saturated regions can be regarded as masking the short LDR input patches, we use mask strategy to reconstruct an HDR image and address saturated problems from one LDR image. Specifically, we use the low exposure image to generate differently exposed images and mask them randomly as the input. Then to train the network, we design a self-supervised framework that forces the outputs to be similar to differently exposed images. After this, we will obtain the pre-trained network. This self-supervised approach allows the model to recover the saturated regions with the capability to effectively learn a robust representation for the HDR domain and map an LDR image to an HDR image. Based on the pre-trained network, we fine-tune the pre-trained model with a few labeled samples. Then, we iteratively refine the model with labeled samples and generate the pseudo-labels of unlabeled data. Considering that the HDR pseudo-labels inevitably contain saturated and ghosting regions, which deteriorate the model performance, we propose an adaptive pseudo-label selection strategy to pick high-quality HDR pseudo-labels to avoid awful pseudo-labels hampering the optimization process. Specifically, we calculate the loss between output and original medium exposure LDR image in well exposure regions and set an adaptive threshold to select more reliable samples. We conduct several experiments. Due to insufficient labeled samples, large motion, and saturation, most comparing methods suffer from color distortion and ghosting artifacts in these datasets. Kalantari's method and deep HDR produce undesirable artifacts and color distortion. Although HDR and AD propose to suppress motion and saturation with attention mechanisms, they cannot reconstruct ghost-free HDR images with few labeled samples. FSHDR still suffers from ghosting artifacts because it is difficult to handle both ghosting and saturation problems simultaneously, and leaves an obvious hand artifact in the car. Thanks to the proposed method, we can reconstruct ghost-free HDR images with only a few labeled samples, which obtains the best visualization effect on individual datasets and cross-datasets. We report means and 95% margin of variations for 5 and 1-shot cases across 5 runs. The proposed method also achieves the best quantitative results on Kalantari's and WHO's datasets, while most other methods perform poorly with only a few labeled samples. We show that our proposed method surpasses the second-best method by 0.15 dB and 0.21 dB in terms of PSNRL and PSNR-mu for the 5-way 5-shot setting on Kalantari's dataset, and it also improves by 0.28 dB and 0.26 dB for 5-way 5-shot setting on WHO's dataset. We further compare our method with major HDR deghosting approaches in 0-shot setting S1, few-shot setting S2, fully supervised setting S3 and cross-dataset setting S4 and S5. As shown in table, our method achieves state-of-the-art performance among these datasets with different settings. It demonstrates that our method not only performs well in individual datasets but also generalizes well across different datasets. We conduct ablation studies under the condition of 5-shot scenario across 5 runs and analyze the importance of each component. All components can improve the performance.